Key for bonus quiz 2 will be up soon. Bonus quiz 2 was, of course, due yesterday. And a week from yesterday, which means next week Tuesday, quiz 3. Now, a fine point regarding the operation, successful operation of voltaic cells. Electrochemical cells which are designed to deliver usable electrical energy, like batteries. For example, yesterday in discussion class you talked about the operation of the lead storage battery. When I first wrote about this subject in the notes, I discovered, as usual in general chemistry textbooks, you don't get any details. So I've always argued that in order for a voltaic cell to operate successfully, to operate without a short circuit, you have to physically separate oxidation and reduction. Now that statement is true. But it's true to the extent that the stuff which is the reducer has to be physically separated from the stuff which is the oxidizer. Because if the stuff which is the reducer touches the stuff which is the oxidizer, then, like we saw when we put a strip of zinc in a solution containing hydrated copper ion, you have a short circuit. Because the electrons transfer directly from the reducer to the oxidizer. Now, what I overlooked is that certain certain voltaic cells, like the car lead storage battery, do not have the half cells physically separated. They do, however, have the reducer physically separated from the oxidizer, which must be true. So how can we look at an operating voltaic cell and recognize when the cell compartment, the half cell compartment components have to be physically separated, and when it's not necessary to physically separate the half cell compartment components? In particular, what I'm talking about are the solution species. With the lead battery, lead is the reducer, lead sulfate is the oxidation product. Lead dioxide is the oxidizer, and lead sulfate is the reduction product. But all these materials are part and parcel of the same solution system. So long as lead, the reducer, does not physically touch lead dioxide, the oxidizer, you will not have a short circuit in the operation of your lead storage battery. Do you recognize that the components of the system, the lead storage battery system which we just described, are all materials which are not in solution? Lead, lead sulfate, lead dioxide. All these materials are not in solution. The lead sulfate can be looked at as a precipitate. Lead is simply lead metal, and lead dioxide is a solid oxide containing lead in the +4 oxidation state. So regarding the conversation about this that I've offered in the notes at the top of page 2218, I noticed the example which I offered is not to the point. Specifically on page 2218, I'm talking about this reaction, where zinc, in the presence of water, hydroxide ion, reduces this stuff, iron 3 hydroxide. Converts the iron 3 hydroxide to iron as the reduction product, and zinc is oxidized to zinc hydrated hydroxide as the oxidation product. Do you see the analogy or the analogous nature of this system to the lead storage battery system? Solid, the reducer, not in solution. Solid, not a well-defined solid, an amorphous, junky stuff, but still not in solution. This is the oxidizer. Reduction product, solid. Oxidation product, solid. None of these components of the reducer, conjugate oxidizer, oxidizer, conjugate reducer, none of these things are in solution. So in order for this system to operate successfully, all you have to do is to keep this stuff, the zinc metal anode, away from this stuff. As long as the zinc metal anode does not touch this stuff, you won't have a short circuit. So here is a case where this system can all operate with the same solution ingredients. So this example is not good. I'll change it when I rewrite this. Perhaps I've made this comment before. For me, one of the real fun aspects, one of the intellectually rewarding aspects of doing this teaching business is every time I go through this, I learn more. I like that. To me, that's fun. I don't know anything that's more personally rewarding than learning stuff. However, so I wrote here, half cells need not be completely separated. Just be sure that what does not contact what. I told you in this conversation. Zinc, the reducer, the stuff that gets oxidized, is not in contact with this stuff. The oxidizer, the stuff that gets reduced. As long as that condition is maintained, you won't have a short circuit. But how about this system, which we've talked about previously? Can I operate this system with a single solution? Or must the solution components be physically separated for this system to operate as a cell which will deliver usable electrical energy? I mean, clearly if I stick a zinc bar in hydrated copper ion, we know a redox reaction occurs, but that's a short circuit system. Spontaneous redox system, but not one which, as constructed, will deliver usable electrical energy. Here, you've got to maintain physical separation of the solution components. Because if these things are in the same solution, you have a short circuit. Because then the anode, will be sticking in the solution that contains this. And there's the short circuit. No good. So here you've got to physically separate the half-cell systems entirely, as opposed to this. So if for the system in question, you just look to see if reducer and oxidizer are solution species or not solution species, you can make a decision about the necessity of having to or having not to separate physically the half-cell systems. My apologies for not noticing that when I wrote this. In any case, now we get on with electrochemical arithmetic. Some of you discussed this, at least in part, yesterday. Some did not. And I want everybody to get the same basis, so we'll back up to this point. There are two general aspects to electrochemical arithmetic whereby we deal with redox reactions from a quantitative standpoint. Faraday's law, or Faraday's equation, and the Nernst equation. First, Faraday's law. In the main, Faraday's law is applied to electrolysis redox systems, where you run an electric current through a solution containing something that you wish to reduce. or an electric current through a melt of something like a molten metal oxide that you wish to reduce in order to get the pure metal itself. So Faraday's equation applies to an electrolysis cell, which is the opposite of a voltaic cell. Voltaic cells is a system that operates spontaneously, and if properly designed will give us usable electrical energy. To operate an electrolysis cell, you've got to put in the electrical energy to make happen what you want to happen. And in particular for Faraday's law, or Faraday's equation and its application, here's what you need to pay attention to. Dimensional analysis. In fact, by now I trust you've recognized that for every problem-solving activity where arithmetic needs to be done in science class, you're always doing dimensional analysis. You can't avoid it. What does dimensional analysis mean? In a nutshell, what does it mean? Pay attention to the units. If you write a setup that A generates the unit or units that the statement of the question demands, and with the data supplied, or data you've had to go get someplace for which to make your setup, if the arithmetic operation indicated by the setup you construct generates the unit or units called for, you got it right. With dimensional analysis, you can solve bundles of problems which may well be about materials or considerations which as yet you have not talked about at all. Squiggle bumps for hoo-ha. Who cares what it is? If it says calculate swiggle bumps, you put down together the units until you get swiggle bumps. You got it. And if the setup you create does not generate the required units, as indicated by the question, I don't care what you do with the numbers, it can't be right. That's why units always come first from a consideration standpoint, from an analyze the problem standpoint. From when you read the problem, you ask yourself, what the heck units is this thing asking me to get? If it's a problem that involves calculation. That's what you have to do. I trust you heard that in 2045. Now then, Faraday's law, or Faraday's equation calculations, involves the Faraday, which is mole of unit charge. The total electric charge borne by 1 mole of electrons. 6.02 times 10 to the 23rd electrons. And each electron bears a charge of 1.6 times 10 to the minus 19 coulombs. Perhaps you heard about that in 2045. In 2045, did you perhaps talk about the famous Millikan oil drop experiment? Where Millikan, in fact, tackled successfully determination by experiment of the charge on a single electron? Did that in 1908. Very interesting experiment. Got the Nobel Prize for that. In any case, there's the total electric charge on a mole of electrons, where C is the unit coulomb, a unit of charge. And here's the Faraday equation, which perhaps you've noticed is on the information sheet. Yeah, I don't hold you responsible for memorizing this stuff. I hold you responsible for being able to use it, which means you got to understand what this thing means. And if you do not think from a dimensional analysis standpoint, and I write a version of Faraday's equation, which is this, so that you have to calculate formula mass rather than mass of material deposited by electrolysis, or electric charge, or time required. Because this thing, which I should have written up here but didn't, the Faraday, is also this, because a coulomb is the product of amperage times time expressed in seconds. So with this, all kinds of variations of the theme. You can be asked, how long does you have to run this electrolysis to produce a given quantity of desired material? What current must be maintained for A amperage? What total charge must be transported for C coulombs? All that stuff. So unless you know dimensional analysis, as soon as I rearrange this, you're going to say, ah! And I don't want that. So, Q is charge in coulombs, which is the product of amps times seconds. Squiggly M is formula mass. Molar mass, same thing. F is the Faraday. Here's the Faraday. And N is moles of electrons transferred. And there's only one way to determine the value for N. And that's to consider the redox reaction that you are trying to make take place by providing electricity to the system. For example, if you have a solution containing hydrated copper ion and you wish to plate copper at the cathode, you want to get yourself a sample of pure copper metal. Per mole of this reduced, you've got to supply 2 moles of electricity, N is 2. It's the way you get in. There's no other way. So we'll take a look at a couple of example calculations which really take off from the couple of discussed examples that you have regarding Faraday's law in the notes, starting on page 2219 and carrying on to page 2220. This discussion begins with imagining that you run an electric current through a silver nitrate solution. And the first thing you might ask is, if I run an electric current through a silver nitrate solution, what will I produce at the cathode, if anything? If I run an electric current through a silver nitrate solution, what if it's a silver nitrate solution, a copper nitrate solution, and a zinc nitrate solution, all mixed together in the same beaker? A zinc sulfate solution, copper chloride solution. Oh, I don't want to put copper chloride solution with silver nitrate because then I'll turn the silver ion into silver chloride. So forget the chloride ion. How are you going to decide, if you run an electric current through a solution like that, how are you going to decide what you will obtain at the cathode if you don't know?
The strongest reducer in the system.
The strongest what?
Reducer?
No, oxidizer.
Oxidizer. You pick out the strongest oxidizer. So once again, as is always the case, when you're going to deal with a chemical system, what do you do first? PSI. That's it. And now you're going to look at this PSI from a reducer strength, oxidizer strength standpoint. Now for Faraday's law, you're looking for oxidizer strength. The stuff in the system which is the strongest oxidizer for sure is going to get reduced, if anything. If you can't reduce the strongest oxidizer, the stuff which is most easily reduced, then you're not going to reduce anything. Just like acid-base system. If H pluses are going to be given, they're always going to be given by the strongest acid present at appreciable amount or concentration in the system. That's just a statement of horse sense applied to the system. So what do you have to do? You make your PSI and take a look at what you got, and for this case, pick out the strongest oxidizer. And if you look at the table of half reactions and you see that you have a solution containing silver ion, copper ion, and zinc ion, you can recognize at a glance that silver ion is the most easily reduced. Silver ion is by far the strongest oxidizer of these 3 metal ions: silver ion, copper ion, zinc ion. What about water? That's in there too. And if I do reduce water, what am I going to get? We've been through this. If you reduce water, what are you going to get? I'm listening. You're going to get what? If we reduce water, we did this by demonstration. You get what? Hydrogen gas and hydroxide ion. Bingo. So if you want to answer the question, am I going to reduce water, or instead am I going to reduce silver ion? You look at the table and see what's easier to reduce. And you see that silver ion is a heck of a lot easier to reduce than water. All right. Question 18 is a follow-up to what you see on page 2220 in the notes, where in the notes a zinc battery is described. This battery depends on the oxidation of zinc. And the battery is indicated to be made from 2.5 grams of zinc, and it delivers a 1 amp current. So the question that I'm referring to, question 18, says, let's imagine I want to make this battery from aluminum rather than zinc. So I'll write down in shorthand, make that from Al rather than Zn. I'm going to make an equivalent battery. In other words, I want a battery which will deliver the same current and have the same lifetime. Same current, same lifetime. How many moles of aluminum do I need to use to fabricate this battery? How many moles of aluminum do I need to fabricate the battery relative to the corresponding zinc battery? Well, when zinc is oxidized, what oxidation state do we develop? Because I expect you know this. You're supposed to learn this in 2045. Zinc shows only one positive oxidation state in its chemistry. What is it? +2. And aluminum shows only one positive oxidation state in its chemistry. What is it? All right. So this tells me, if I make one battery using a mole of zinc, 1 mole, and I make the other battery using a mole of aluminum, 1 mole zinc battery, 1 mole aluminum battery. If the batteries last the same amount of time, which battery gives me more electrical energy? Aluminum. Because per mole I get 3 moles of electricity per mole of aluminum oxidized. Per mole of zinc oxidized I only get 2 moles of electricity. So, if I want to know moles of aluminum compared to moles of zinc in order to fabricate this battery from aluminum rather than fabricating the battery from zinc, I'm going to write down and there's dimensional analysis at work. Tells me moles of aluminum to moles of zinc. 2 to 3. All right? And now, if I want to factor in this mass quantity, if I want to know how many moles of aluminum am I in fact talking about? I have to go back and recognize that I made the original battery from how much zinc? 2.5 grams. And as things stand, I got a ratio of moles of aluminum to moles of zinc. And now I want to factor in this 2.5 gram sample of zinc and find out in sum how many moles of aluminum corresponds to 2.5 grams of zinc. What factor must I also consider as I write my setup? Molar mass of what? Zinc. You learned in 2045, didn't you? If you want a relationship for any chemical substance between mass and moles or moles and mass, either way, you must consider formula mass. So, for zinc, as I carry on in developing this setup, do I write mass per mole or mole per mass? Mass per mole or mole per mass?
Mass per mole.
If I write mass per mole, I'm going to get moles squared in the denominator. What the hell does that mean? Dimensional analysis. You've got to let this stuff talk to you. So I got to write moles per mass. Right? And I think this is right as the molar mass of zinc to 3 sig figs. And now, I can at last complete my setup by adding that remaining factor upon which this entire calculation depends. And what is that remaining factor? What is it?
Grams of zinc.
It's the amount of zinc that was used to fabricate the original battery. And what do I wind up with? Moles of aluminum. So I found out how many moles of aluminum is in fact equivalent to 2.5 grams of zinc, electrolytically speaking. And if I want to convert this into mass of aluminum, what do I do now? Multiply by grams per mole for aluminum or moles per gram for aluminum? Grams per mole. It's just dimensional analysis. There's no other way. And I will tell you, once again in my humble opinion, which I'm sure you know is any damn thing in the universe but humble, textbooks are really stupid when they try to show you how to do dimensional analysis. Because they start back asswards. They don't start with the unit or units that the question or problem demands that you get. That's what you have to start with. Because at least you're starting so as to respond to the question asked. These are the units I have to get. I start with them. And ultimately I will get at the factor upon which the calculation depends. Textbooks invariably for this question will start with this. I don't know where I'm going then. But if I start with this, I know I'm on the right track because doggone it, the question asked me to get moles of aluminum equivalent to a sample of zinc. So I want to start with this. I know I'm on the right track when I do that. That's the way to do dimensional analysis. Fortunately, this aspect of dimensional analysis was in fact taught to me by my general chemistry instructors way back in the fall of 1960 at the University of Toledo. How about that? You know, ancient history. Hieroglyphics. Non-calculator. All right. This is 18. 19. 19 says, let's talk about a metal chloride which has this general this general composition. 3 moles chloride ion per mole of metal. Formula tells us that. We want to know what the metal is. So what are we going to do to find out? We're going to melt this metal. So I'll use this symbol, which chemists often use to indicate the addition of heat. And turn it into molten MCl3. And now I'm going to run an electric current through this system. It melts in here. What am I going to make at the anode? What am I going to make at the anode? Chlorine gas. Chlorine gas has got a lot of useful industrial purposes. And when we want to make chlorine gas, to my knowledge, this is the way it's made. To try to make chlorine gas chemically is very difficult. Why? Because chlorine is too strong a... What?
Too strong a reducer.
Reducer? Oxidizer. Remember we talked about fluorine when we looked at our redox table, our half reaction table? Said forget it trying to make fluorine chemically. There's nothing strong enough to oxidize fluoride ion. Fluorine is the best oxidizer known, practically speaking. Chlorine isn't far away. And at the anode, we're going to make the metal. All right? The statement of the question goes on to say, we make 2.695 grams of metal. What am I trying to do in order to determine what the metal is? Calculate its formula mass. Grams per mole. So what am I going to write down first? Dimensional analysis. I'm looking to get grams of this metal per mole of the metal, right? That identifies the metal. Then all I got to do is get out my periodic table and see which metal has this grams per mole property. So what am I going to write down first? Grams of the metal. All right? And now I want to write a factor which will have what in the denominator? Moles of this metal. Damn right. What's on top? See that formula? What's that formula tell me? What does this formula tell me? This formula tells me that the oxidation state of this metal is what? Plus 3. So I'm going to write down this. You agree? So what am I writing here? 3 moles electrons. That's dimensional analysis. You try to do it by just memorizing this, you got troubles. I mean it. Because what we're doing is to show you how we can succeed with this if we understand this thing. If you don't understand that, forget it. And now, my dimensional analysis knowledge tells me I've got to write another factor which will eliminate from what I have here so far what? I got to get rid of this. Well, what is a given regarding these electrolysis calculations, Faraday's equation application, that contains moles of electrons? The Faraday. How about that? Here it is. There goes moles of electrons. Now then, the question also says that I electrolyzed this with a 10 amp current and I ran this current for 25 minutes. What am I going to do with this current information and time of electrolysis information? Well, we'll talk about, never mind the unit conversion. I want to know what we're going to do with the time the electrolysis is run and what we're going to do with the current used. Are we going to divide by these materials, these quantities, or multiply by these quantities? Divide. It's dimensional analysis. I got amps thinking of here, and I got to get rid of that stuff. What's this current? I forgot what it is. 10 amps? Is that it? There's amps. What was it, 25 minutes? So I got to make one more unit conversion. Watch out, this is tough. How many minutes in a second? Done. And this is the way to do it, and there's no other way if you want to be successful. Now you can get out the grinder, means your calculator, push the buttons, and I'll get 52.0 grams per mole. Now again, this table unfortunately has no formula mass information, but in the notes you have a periodic table that's got formula mass information, as well as on the information sheet. You'll find out this mysterious metal is chromium. Cr. Now, question 20. Question 20 is just like question 18. We're going to ask about the electrolysis of magnesium chloride as opposed to electrolyzing what we now have determined to be chromium chloride. Okay? If I make a melt of magnesium chloride and I electrolyze it with the same current for the same amount of time, that's question 20. Will I get more magnesium or less magnesium? Now watch out about this more or less, because I can answer this either of two ways. What are the two ways? I can talk about moles of magnesium, or I can talk about grams of magnesium, mass of magnesium, right? You think I'll get the same answer both times? What property of magnesium do you think we need to pay attention to wrestle with this issue? Oxidation state, and what else? Formula mass. If you look up the formula mass of magnesium, you see it's 24.3 grams per mole. 24.3 grams per mole. Now I've already done enough, I should think, based on my analysis of question 18, to realize that if I electrolyze this for the same amount of time with the same current, will I get more moles of magnesium than I got moles of chromium here?
Yes.
By what factor? 3/2. Bingo. I get more moles of magnesium. Now, when I electrolyzed the chromium chloride, I got 2.7 grams practically, okay? Instead of 2.695, we'll call it 2.7 grams. Am I going to get a sample of magnesium which has a mass greater or smaller than 2.7 grams? Smaller. And I don't need any fancy arithmetic. Do any fancy arithmetic to support that conclusion? All I need to do is to look at the molar mass of chromium, 52.0 grams per mole, compared to the molar mass of magnesium, which is 24.3 grams per mole. And I recognize that the ratio is far greater than 3/2, which tells me the mass of magnesium which I obtained by this process is smaller than 2.7 grams.
How do you know it's 3/2 and not 2/3?
It?
You said
Look.
by factor of 3/2. How do you know it's not 2/3?
If I'm going to reduce MCl3 to make chromium metal, okay? We wrote this down someplace. Per mole of this produced, I got to put in 3 moles of electricity. But if I want to make magnesium, per mole of magnesium produced, I only got to put in 2 moles of electricity. Well, if I run the same current for the same amount of time, needing only 2 moles of electricity here, well then, I got to make 3/2 moles of magnesium. Right? I needed 3 moles of electricity to make my sample of chromium. So however much magnesium I make is going to be 3/2 times as much, because of the electron requirement to turn magnesium ion into a mole of magnesium relative to turning a mole of chromium ion into a mole of chromium. I put a +1 ion in here. Hey, now I'll make 3 moles per mole of chromium. All right? Enough on that. We go now to what is by far, I think, the most common electrochemical arithmetic consideration, the Nernst equation. The derivation of the Nernst equation is in the notes. It all comes from this, which is the change in free energy for the reaction under any set of conditions, and this. Which is the change in free energy for the reaction under what conditions?
Standard state.
Standard state conditions. Which means, if you're running an electrochemical cell under standard state conditions, every solution species is present, at least initially, at what concentration? 1 molar. And every gas that's part of the system is initially present at what partial pressure? 1 atmosphere. Bingo. Now then, when we operate on these relationships, you get this. E cell equals standard E cell minus 0.059, we can go to more figs, but that's not necessary, times V volts over N times the log of Q. We know what Q is. It's the reaction quotient. I didn't do this. The electrochemist did this. Don't get this Q, reaction quotient, mixed up with this Q, which is charge. I think when I rewrite this, I'm going to use small q for charge. Because I think small q, for example, is what you used. No, small q is for heat. All these, we got too many things going on in science. We got to invent new symbols. I don't know, I'll cook up something. All right? And you know how to write Q. That's an expression which is exactly of the same form as the equilibrium constant, except that it pays attention to any imaginable set of conditions. Now then, before we engage in any electrochemical arithmetic, question. If I operate an electrochemical cell at standard state conditions, what is E cell? If I operate an electrochemical cell at standard state conditions, what is E cell? What is it? What is it? If I'm at standard state conditions, what's the log of Q?
0.
Because Q is equal to 1 at standard state conditions. So at standard state conditions, E cell is the same as E0 cell. Now, the most common application, or at least one of the most common applications and uses of the Nernst equation, is to calculate, guess what, equilibrium constants. And one of the questions we're going to talk about next time is the calculation of equilibrium constant, specifically the KSP for ferrous hydroxide. It's in the questions, don't worry about it, it's question 26 or something like that. If I am using the Nernst equation to calculate an equilibrium constant, what is the value for E cell? What is it? Louder! 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 0! Right? Equilibrium constant. E cell is nothing. It's not going anyplace. Now, one more comment. Take a look at the half reaction table. When you examine the half reaction table, please take a look specifically at half reactions 23 and 39. Now, these two half reactions are also in the list of half reactions on the information sheet, but the information sheet list is an abbreviated list, because I don't want to be handing out 2 information sheets for an exam. Too much monkey business. So they have different numbers on the information sheet. Notice, please, that the information in the notes tells you that the voltage values tabulated for half reactions 23 and 39 are not E0 values. They're E values. Because half reactions 23 and 39 have potentials cited under what pH conditions? It's in the notes, look. pH 7. Is that standard state? No. What pH conditions correspond to standard state? pH equals 0 and what else? pH equals 14. Oh, you got hydroxide in 1 molar. The other one is hydronium in 1 molar. Pick it up from this point next time.